Welcome to the start of Chapter 3, which is all about polynomial functions. In this 3.1 video of graphs of polynomials, we'll be talking about the basics of polynomials. So we'll be defining a polynomial, talking about its domain, as well as a lot of polynomial vocab, degree, leading coefficient, leading term, constant term. We'll also talk about the end behavior, and at the end we will name polynomials. So there's a lot in this video, but it is going to be broken up using the chapters feature on YouTube, so hopefully it will be less crazy to navigate if you need to look back at anything. All right, so let's define a polynomial. I'm taking this straight from your book and going to break down the definition. It is found on page 235 in your textbook. Here is the definition of a polynomial. It looks scarier than it really seems. It is a function, and it's in this form. So we have a bunch of different terms separated by either plus or minus signs. In math, we put plus because subtraction is really just addition of a negative. So we use plus in terms of plus or minus. And these coefficients here, a sub n minus 1, a sub 2, a sub 1, a sub 0, those just are telling us the coefficients, and they're just the numbers in front of the variable. And they have these little subscripts here because this is saying that this is the constant term, so it's 0. It's like the term with x to the 0. There's no x. A sub 1 is the term linear constant, so it's the coefficient out front of the x sub 1 term. A sub 2 is the coefficient in front of the squared term, and so on. We don't know how big the polynomial is, so we just start with a sub n and x to the n to represent any number. And it's going down until we get to 2, 1, and then nothing. So those a's are elements of the real numbers, meaning they're just real numbers. This means an element of, so it's a part of, the reals. And then our n's, the exponents of x or whatever variable, those are natural numbers. They are elements of the natural number set, which is a little like n with this double line here. And that just means that they have to be positive integers, so they can't be decimals, fractions, negative, or 0. So n could be a number like 5 or 3 or 1 or 17, but it couldn't be 1/3 or like -2 or 0. All right, so that is the definition of a polynomial. All right, the domain of a polynomial is all reals. So the domain of a polynomial is all reals, and of course we know from experience that we can write that as from -infinity to positive infinity. All right, let's identify if each one of these is a polynomial. I'll just go one by one. So is f of x a polynomial? Is it made up of terms where the coefficients are real numbers, or the constant? So 3 is a constant, it's a real number. -1 is the coefficient here of our quadratic term. -1 is a real number. And are all of our exponents natural numbers? 2. Yes. Is the domain all real numbers? Yes. There's no x in a denominator or x under a square root. So this is a polynomial. Okay, is g of x a polynomial? Is it made up of terms separated by plus or minus? Yes, it's made up of 3 terms. Are all of our coefficients or constants, are all of those real numbers? Pi, -3, and square root of 2. Yes, they're real numbers. Even though pi and root 2 are irrational, they're still real. Are all of our exponents of our variables natural numbers? 5 and 4 are both natural numbers. And lastly, is the domain all real numbers? Yes, we have no x in a denominator or no x under a square root. Therefore, g of x is in fact a polynomial. All right, let's take a look at h of x, and you'll note off to the side I made like a little checklist since I feel like I'm talking too much and I need to write that down. So let's take a look at h of x. Are the coefficients all real numbers? 12, -1, and 1. Yes. Are the exponents all natural numbers? 3, 2, and 1. Yep. Is the domain all reals? No. In this case, we do have x in a denominator, therefore the domain is all reals except 0, and that can't be. Now, couldn't you argue that you could simplify this, right? In the numerator, you could factor out an x squared, and you'd be left with 12x minus 1, and then down here you'd have an x, and then an x can cancel, so x, and then you'd be left with x times 12x minus 1, and then you could distribute that x back through, and you'd have 12x squared minus x, and that looks like a polynomial, right? The domain's all reals of this. Okay, sure, but in order to find domain, you have to start at the very beginning. So even if you can cancel out an issue and write it more nicely, the domain has to be found from the very beginning. So h of x is not a polynomial, because the domain is not all real numbers because of that guy down there. The next attribute of a polynomial that we'll look at is its degree. The degree of a polynomial has to do with its exponents, and I hate saying that the degree is always the largest exponent because it does depend on how our polynomial is written. So we experienced different forms when we talked about quadratics, and quadratics are just a specific type of polynomial, but a polynomial can be written in standard form, which are the ones we've seen so far, or actually in factored form, which we'll get into more in this chapter. So let's take a look at the standard form side of this first, and then we'll take a look at what factored form means. All right, let's take a look at f of x. This is in standard form. It's just written with no parentheses, like no factors, and the terms are all separated by plus or minus. So standard form means that the terms are like written in order, so the highest exponent's written, the largest exponent's written first, and then it goes in descending order, which it does. So the degree of this polynomial would be 4. It's a quartic polynomial. It's 4 because it's in standard form, and we look for the largest exponent. So the degree of this polynomial is 4. All right, g of x is also a polynomial written in standard form, and this is just a linear polynomial, right? A linear function. It would just be a line, mx plus b, and a line is just a type of polynomial. So this degree here would be 1 because the largest exponent's 1. We just don't write it. So this polynomial, g of x, has a degree of 1. And then I have one more example that I put here because I ran out of room. So h of x equals 7. This is a constant polynomial. It's just a horizontal line. And the degree here is actually 0 because this could be written as 7x to the 0. It's just the constant term. So this is still a polynomial and it has degree 0. All right, over on the factored form side here, this is a polynomial written in factored form, and you can see that the terms are not separated by pluses or minuses. They are like inside each factor. This f of x has 3 factors. X squared is 1, 2 minus x is another, and x plus 1 is the third factor. We want to look at all of the exponents, so we can see that here the exponent of this factor is 2, the exponent of this factor is 1, and the exponent of this factor is 3. So we want to add those all together. The reason that we add those together to get the degree of 6 is because if you were to multiply this out, which would take some time, that would take a while, if you were to multiply x squared through, right, then you'd have to multiply x plus 1 times itself 2 more times, right, cubic, and then like all that multiplying out, your first term would end up being an x to the 6th out front. And so basically, if you were to get this into standard form through a lot of multiplication, its largest exponent would be 6. So that's why we do a quick thing of just adding the exponents. All right, let's take a look at g of x. This one is also in factored form. And we can see that we have 2 factors. One factor is 3x, the other factor is x minus 7. And each one of these has an exponent of 1. So our degree here would be 1 plus 1, which is 2. This one would be very easy to multiply out, right? If you distributed the 3x, you'd have 3x squared minus 21x. And so in standard form, the largest exponent would just be 2. Anyway, that's why we add them together. So again, I hate saying the degree is always the largest exponent because again, it does depend on if you're in standard or factored form, but these are really just the 2 ways to find degree. And if you were to multiply your factored form out, it would end up being the largest exponent. So adding them together is just a quick way of doing that without all that multiplication. The next couple things that we'll look at in polynomial basics are identifying the lead coefficient and the lead term. Sometimes these are called leading coefficient and leading term. I just don't love writing all that, so your book I think calls them leading. Anyway, so let's take a look at standard form examples and again factored form examples. Standard form examples, those ones are going to be real easy to identify the leading coefficient and term. Factored form will take a little bit more work with some multiplying. Okay, I'm just going to take a look at two examples for standard form. This isn't too bad. So the leading coefficient, we have to understand that coefficient is just the number that's in front of the variable. It's not the variable itself. So standard form, again, if something's written in standard form, it's already going in order. Sometimes you might not have something written in perfect standard form, like these two might be switched around. You just have to be careful that well, we'll get there in a second. All right, let's take a look at f of x. So our leading coefficient, we want to make sure that we're looking at the term that has the highest exponent. And in this case, that biggest exponent is just 1. This is just a constant over here. Its exponent is 0. So our leading coefficient, LC, is going to be -1/8. And our leading term is just the whole thing. It's the whole term. It's -1/8 x. So there's not like a ton of difference. The term is just all of it, and the coefficient's just the number. Okay, moving on to g of x down below, we see that the term, this is in correct standard form, and it's descending order of exponents, and so our leading coefficient is technically the number out front. It's 6, whereas the leading term is the whole term. It's 6x to the 4th. So that's, I don't know what more to say about it. It's not too difficult. All right, factored form will be a little bit more challenging here. All right, this example will take up a little bit more space, and I'm actually going to look at the leading term first. We have to think about if this were being multiplied out. It is extremely, it's wrong to just say the leading term is 3x squared, because technically if this were to get all multiplied out, the leading term would be something greater than that. So what we have to do is look at the leading term in each individual factor. Let's take a look at what that means. I'm going to underline that in blue. So this first factor, 3x squared, that's its own leading term, okay? Then the leading term in this middle factor here is a -1, and it's just, -1x, and it's only -1x. It's not being raised to anything more than 1, so it's just -1x. So I'll underline that. But this last factor here, if you were to multiply x plus 1 out to the 4th, it would be something long. But let's look at the leading term in here is just 1x, and if you were to raise that to the 4th, it would be 1x to the 4th. So this is really 1x to the 4th. All right, so our leading term, what we need to do is multiply those leading terms. So it's 3x squared times our -1x times our 1x to the 4th. Now, how do we multiply those together? We first multiply the coefficients together, which is 3, -1, and 1, which gives us -3. And then next, we multiply x squared times x to the 1st times x to the 4th. We add our exponents for rules of exponents, and we get -3x to the 7th as our leading term. So that's our leading term. Again, getting that as if we were to multiply this all out, but you don't have to multiply all of it out. You can just multiply the lead terms of each factor to get the overall leading term. Now, what's our leading coefficient? That's easy enough to see. It's going to be the coefficient of our leading term, which is -3. That's why I like to do the leading term first, because it's easy to see what the lead coefficient would be after that. Let's look at another example. In this next example, g of x, we again have a factored form of a polynomial with 3 distinct factors. Let's first find our leading term by multiplying all 3 leading terms together. So our 3 leading terms are going to be -1x. Then this one is going to be 2x cubed. So the leading term there is 2x, but it gets cubed. 2 cubed is 8, and x cubed is x cubed. Then our final one is going to be x squared, so our final leading term is x squared. There's a 1 out in front, and that one doesn't change. So our three leading terms that we have from each factor are negative 1x, and 8x cubed, and an x squared. And those are going to get multiplied together for our final leading term, which will leave us with negative 8, and that's a 1 right there, negative 8x to the 6th when we add our exponents. So that is our leading term, leaving our leading coefficient to be negative 8. The next major thing about polynomials that we need to discuss is called end behavior. And the end behavior of our polynomial is how its graph behaves at the ends, which are to the right and to the left. Let's take a look at this cubic polynomial I sketched down here. We can see that on the right end of the graph, as x gets larger and larger, I will label the axes here. Of course, that's our x and that's our y. As x approaches positive infinity, and we look to the right, as x gets larger and larger, our graph is going up. It's approaching positive infinity. And of course, the graph is called f of x. It's our function. And then as we look to the left, all the way over here, as x gets very small and as x approaches negative infinity, when we look to the left, our function is going down to negative infinity as well. Here's how we write end behavior. Here's how we write R-I-G-H-T, end behavior. Looking to the right means as x approaches positive infinity. So we write as x approaches positive infinity, what does our function do? That's a comma. Let's write that nicer. As x approaches positive infinity, f of x approaches something. And in this specific case, for this one, our graph f of x is approaching positive infinity because it's going up. So this is for this example here that I've sketched. Then our left end behavior, we'll do in dark blue, is when we look to the left. That is when x approaches negative infinity. And we use the word approaches to like say out loud the arrow. Our function f of x is actually going towards negative infinity as well because it's going down to the left. Let's actually take a look at another example, and I'll sketch a different graph this time. All right, this time I'm going to sketch a positive quadratic function, a parabola. Note that I have erased here. This stays the same all the time. Like to describe right end behavior, it's as x approaches positive infinity because it's as we're looking to the right. And then we say, what is our graph doing? This is the part that we need to fill in. This is our left end behavior always. As x approaches negative infinity, it means we're looking all the way to the left and seeing what our graph does. So let's take a look at our quadratic here. We can see that as x gets larger and larger, as we look to the right, what is our function doing? Our function is going up. That means our function is approaching positive infinity. Then, over here, as we look as x gets smaller and smaller as it approaches negative infinity, meaning we look to the left, our function is also approaching positive infinity. So both of our end behaviors go to positive infinity. Let's look at one last example. All right, in this last drawn example, we can see that we have another polynomial function. And our right end behavior, again, is described as x approaches positive infinity. What's happening to the right? Our function f of x. I think I forgot to write that in last time. Our function f of x is actually going down. So we say that our right end behavior is towards negative infinity. And that's how we write our right end behavior. Then I'll write the left end behavior in navy blue. As we look to the left, as x approaches negative infinity, our function's doing what? Our function's going up, so it's approaching positive infinity. Now, how do we determine end behavior without looking at a function? We can actually determine end behavior in a more algebraic way by looking at the degree and the lead coefficient of our polynomial. All right, here are the rules for identifying the end behavior. Please note that REB means right end behavior, and LEB means, you guessed it, left end behavior. All right, in order to identify without graphing, we first have to identify the end behavior. We first have to find what the leading coefficient is. If the leading coefficient is a positive number, the right end behavior goes to positive infinity. If the leading coefficient is a negative number, the right end behavior goes to negative infinity. Then, once you've identified the right end behavior, we identify the degree. If the degree is even, that means the left end behavior and the right end behavior are the same. If the degree is odd, that means the left end behavior is opposite the right end behavior. So if you found the right end behavior was positive infinity, the left end behavior would be negative. Let's do an example. All right, let's say we want to identify the end behavior of this polynomial here. The first thing we need to do is identify the lead coefficient and the degree. Then we can identify what the end behavior is. So let's find the leading coefficient. It's in standard form, so these are not too hard to find. So our leading coefficient is -2, and then our degree is 5. Okay, now we should be able to find the right and left end behavior. So let's write out the right end behavior and the left end behavior. And we write them like this. The right end behavior is written as x goes far to the right. As x approaches positive infinity, what's our function doing? And the way we write our left end behavior is as x goes to negative infinity, as we look all the way to the left, what's our function doing? Again, this is always how we write end behavior. What changes is what goes here, because this is what our function does, which changes depending on what the function is. Okay, the right end behavior is figured out by the lead coefficient. Our lead coefficient is negative. That means the right end behavior is negative. So our function goes to negative infinity at the right. Okay, then our degree will tell us what the left end behavior is. Our degree is odd. That means our left end behavior is opposite what our right end behavior is. So our right end behavior is negative infinity. That means our left end behavior has to go to positive infinity. Feel free to graph this and we can totally see. Okay, guess what? I decided to graph it. We determined that our right end behavior was in fact to negative infinity, and whoops, you can totally see that as we go all the way to the right, our function decreases pretty rapidly to the right. It does go to negative infinity. And our left end behavior, as we look to the left of our function over here, our function does go to positive infinity. So the graph will always help you out too. Okay, here's our second and last example for this. To identify the end behavior here, we need to find the leading coefficient. In order to find that, we need to, we can find our leading term, which would be x times x squared times x times 2x squared, which is 2x times 2x, so 4x squared. So our leading coefficient will have a 4 and will be x to the, 1, 2, 3, 4, 5, 6. So 4x, oops, I don't even need the x to the, I'm only doing coefficient, just 4. Okay, then our degree will be 6. Okay, so now we need to look at the lead coefficient to find the right end behavior. It's positive. And that means our right end behavior is positive. Positive infinity. Then our left end behavior is determined by the degree. Our degree here is 6. It's even. That means the left end behavior is the same as the right. So they're both to positive infinity. All right, I'm going to go through 2 examples, one in standard form, one in factored form, of finding all the stuff and putting it all together. So I'm not going to do a ton of explaining here. I'm just going to go through and write them down. So this is a good practice opportunity for you if you'd like to pause here, find it, and then you can check your answer in just a second. Our degree will be 4. Our lead coefficient is 12. Our leading term is 12x to the 4th. Our constant term is -5. That's not something we really talked about, but the constant term, if there is one, is just the term that does not have an x in it, or whatever variable. And then our end behavior, our right end behavior is as x approaches infinity, what does f of x do? And our left end behavior is as x approaches negative infinity, what does f of x do? Our right end behavior is going to be determined by our leading coefficient. It's positive, so that means our right end behavior is to positive infinity. Our left end behavior is going to be determined by our degree. and our degree is 4, which is even, so that means our left-hand behavior is the same as the right. In this next example, we do have factored form, and go ahead and see if you would like to pause the video now and see how you do. The only thing we haven't covered is how to find this constant term, but I want to see if you could figure that out. So if you'd like to practice, go ahead and pause the video now and then hit play to see how you did. All right, here are all of the solutions. Our degree is 5 because we did 1 plus 2 plus 2. Our leading term, I'll start here. We do all the leading terms, so negative 2x times 1x squared times another 1x squared gives us negative 2x to the 5th. Therefore, our lead coefficient's negative 2. Our constant term, this is one we haven't discussed. It's basically the same as finding the leading term. You take all the constants, so 3 squared times negative 1 squared. We'll get 9. Our end behavior, our right end behavior, we take a look at the leading coefficient. It's negative, so our right end behavior goes to negative infinity. Our left end behavior, we have to look at the degree. Our degree is odd, therefore the left end behavior is opposite of that, so it goes to positive infinity. The very last thing that we'll discuss in this video is how to name a polynomial, and it will only make you name polynomials that are in standard form. Polynomials, just like us, will have a first name and a last name. That's at least how I like to describe it. So the first name, I did find this online and I think it looks cute, but a polynomial's first name is determined by the degree of the polynomial. So we've all, heard of linear and quadratic and probably cubic, right? So linear is just a regular x, the degree 1. Quadratic is when we have x squared. Cubic when the degree is 3. And these are y's, by the way. They look like 4s, but they're y's. Then when the degree is 4, we might not have heard this one. It's called quartic. And when the degree is 5, I hardly ever hear this, it's quintic. There are no special degrees names for anything higher than that. So you would just call them like a 6th or 7th degree or 8th degree. Then when we have just a horizontal line, that's called a constant function or a polynomial, just like y equals 3. All right, then a polynomial's last name is determined by how many terms it has. So a one-termed polynomial is a monomial, a two-termed is a binomial, and a three-termed is a trinomial. There's no special name for 4 or more terms. Those are just called polynomials. So polynomial is the overarching thing. All of these are polynomials, and like a trinomial is just a specific type with 3 terms. All right, so let's get to naming a couple. All right, let's take a look at this f of x here. We want to find the polynomial's first name, so we look at its degree. It's degree 4, therefore it's a quartic. Then we look at how many terms it has. It has 3, so it's called a quartic trinomial. All right, this next polynomial, g of x, has a degree of 3, therefore it's a cubic. Then it has 2 terms, so it is a cubic binomial. This last example, we see that the degree is 8, so its first name would just be an 8th degree. Then we see that it has 1, 2, 3, 4 terms, so it's just a general polynomial. If you would like to write polynomial with 4 terms, you can. I normally don't see that, but it's not wrong if you want to write that, but you can just call it a polynomial in general. And oh my goodness, you made it to the end. I know this was a long video. It kind of got carried away from me a little bit, but thanks for bearing with me that whole time, and I hope you learned a lot about the basics of polynomials.